Good morning and welcome to our first Insight stage for the day. And just a reminder that all these Insight stages are being live streamed, so they'll be available on our website as well as YouTube afterwards. So you're welcome to go back and have a look at those if you see something that you'd like to learn more about. But to kick us off today, we've got Penny Stewart from Petra Data Science, and Penny's here to talk about digital twin value chain optimization. So welcome, Penny.
Good morning, everybody. Today I'll be talking to you about a case study. So even though we're talking about the future here, this is very cutting edge. Our latest case study from Banasai mine in Laos, and it's a digital twin value chain optimization. My co-authors are Scott Cowley, who's the General Manager Tech Services of Panost, and the Senior Resource Geologist, James Carpenter. So many of you would have heard of the term digital twin. I'm just going to give a quick definition of what I mean by it using Wikipedia. I checked it last night just to make sure it was still up to date. Digital twins integrate Internet of Things data with machine learning, artificial intelligence, and spatial networks to give you an ability to simulate in a live way a process. Okay. So why would you want to do that? There's a couple of good reasons. The first reason is you might want to be able to see what's going to happen in the future. So that's for preventing downtime or looking at playing forward a process like a schedule and seeing how that schedule is going to play out. And then finally, the other thing that's quite distinctive about a digital twin is the ability to do what-if scenarios. So that's your virtual experiments, right? And I'll give you some good examples of that shortly. Now, to start off, I wanted to talk about geology, because when we talk about value chain optimization in mining, I'm an engineer, a mining engineer. I've got colleagues, metallurgical engineers at Petra. We find that geology, if you can get the geology throughout the whole value chain, you can really start to understand where some of our issues are in terms of why we don't always get the results we're expecting. And on this little example, there's two rocks here. The top rock is the same rock type from the same mine, 5 meters apart. Have a look at that value there, UCS. That's the way we measure strength in rock mechanics. And we use UCS in almost every design aspect in the mine value chain. We use it for geotech, we use it for drill and blast, we use it for SAG mills, crushers, you name it. And have a look at that same rock type, factor of 4 difference. And this is what's underlying, and this is why if you're going to have a digital twin in mining, you need to integrate your data. Okay, so that's why we're doing the integration. We've been doing this now for over 3 years. We actually got a Mining Magazine award back in 2016 for our first case studies in this area. At the time, it wasn't fully productionized, so we've moved from being a study-based approach to a full productionized version, which is now what we call Maxter. We take about 12 weeks to integrate the data, because in mining we don't have standardized data formats, so there's a bit of service work required. And then it takes only an hour to get this into production, so the value up is quick coming forward. These are some of the examples, these are some of the simulations that we've done so far with Panost. So we've done a recovery problem that they have, and I'm going to show you that one in a minute. Drill and blasting optimized to different rock types. And then finally, actual process optimization. So that's the set points in the processing plant. So to do this, the real enabler of this is the ability to track the ore. Because once you can take spatial data and convert it into a time series, that enables you to do machine learning algorithms. And to build our models, we'll typically use a year or two of data. And that will include everything from the geology, drill and blast. It can include weather and other factors that may impact on a process as well. In this case, it's a small mine. It was only 5.12 gigabytes. Sometimes it's a couple hundred gigabytes. So what does that mean? What is the value chain in mining? This is all familiar to us. We've got geology, blasting. We've got load and haul, obviously. We've got liberation. And we've got separation. And then we obviously got metal. So the game here is obviously to maximise the metal produced at the quality specification that you're needing to sell it at. So how do we productionize this stuff? There's a very simple way. If you're looking at your long-term planning, you can productionize these machine learning algorithms into standard mine planning software that all the mine sites use now. We've already done that with Maptech. Maptech is a partner of ours, and so their scheduling engineers now can do optimization, planning, design with the latest recovery predictions, which are based on 2 years of data. So this comes from a paper that they published at the Complex Ore Body Conference last year. This is our drill and blast simulation. You can see that we're predicting versus actual tons throughput. I'll go into that in a bit more detail in a minute. So that's the drill and blast. Mine optimization. Once you've got really, we call it dynamic optimization because a lot of optimization mining has assumptions that aren't based on actual mining feedback loop. So it's dynamic because we're using the actual mine performance in the plant or in the drill and blast or crushers and feeding that back into the optimization so that you get much more accurate forecasting, scheduling, design. Yeah, so that's what it's all about. That gap between what we think we're going to get and what we actually get, this is a real enabler for that. Finally, in the processing plant, we've also got digital twin simulation in the processing plant. I won't go into that one in much detail today, but if you'd like to know more, please come and see me at the stand on that one. This is our machine learning model being deployed into existing mine planning software. This is Banasai mine in Laos. It's a small mine, but it was a perfect opportunity to test out this. Those pink and red blocks are the high tailings grade blocks. That means they're the blocks where they're sending lots of their precious metal out to the tailings dam. And they wanted to know where that is, obviously, because they don't want to send waste to the plant. So this was really important, and this is their case study. They've been presenting this themselves and saying we're managing this situation now. Now we know where the ore is and where it's waste. This is our drill and blast simulation. What we've got here, I'm showing you here, is the predicted versus the actual. This is so that when you're doing a simulation, you actually can see that the underlying model is reasonably accurate, because there's no point doing a simulation if your underlying model is flawed. So then we change the burden and spacing down the bottom using historical data, and we can see what effect that would have. So if you, on average, reduce your burden and spacing in that particular geology, then that's the effect. You would have a slight uplift in the SAG mill throughput, for example. And this is all driven by complex geology. There would be 20 different intrinsic rock properties driving that, every one of those predictions. Right, so I would like now to just acknowledge our collaboration partners, because obviously solving something that's been a bit of a challenge for mining for a number of years hasn't happened without a lot of great collaboration. So we have a project with Mets Ignited that is partially funded by the government and also matched funding obviously by industry. Barrick and McMahon are funding that. We have Panost as our Maxter collaboration partner. And we thank them very much for enabling us to present this case study to you today. I would also like to mention that we are working with other platforms to providers. So Maptech's obviously a really big name in mine planning, but there are plenty of others. MaxMine's a smaller business improvement online. But the point here is that by collaborating with these companies, we can get machine learning into operations really quickly. So that's what I see as missing, is just how long it can take otherwise. And we're trying to identify all the different opportunities to get the dynamic feedback into mining. I think I've got a little bit of time for questions, so that's great. So would anyone like to ask me about this case study or about the Maxter? No? Did anyone want to see that, the drill and blast simulation bit? Ask about that, because I usually get a lot of questions about that one, about understanding what that's actually going on there. I might just spend that time to explain it a bit better. You can change the timeline along the bottom. That's shown on a shift-by-shift basis, but you can change that to weekly, monthly, quarterly, and see what effect it has over different time frames. The other thing is you can change that to be not drill and blast. You can change it to set points in the SAG mill. So we have another version of this, which is about optimizing the set points in the processing plant. So it's up to you which levers. So if you're a mining engineer, you're going to want to look at drill and blast levers and schedule levers that affect throughput of the SAG mill. If you're a metallurgist, you're going to want to see a different set of levers there, and you're going to see what effect they have. And it's all interrelated to related to that geology. Yes, Steve.
Are these models agnostic that you play with?
Yes, so we can play. You mean like, can we play them, put them on any platform?
Yes, so can you be recording any type of schedule for them?
Yes, that's right. All you need to play forward your schedule into a Maxter, and it's a web service, is the time period and then all the blocks in that time period. So that might be, in 1 month, there might be 10,000 blocks. So you send those blocks to the web service, and we send you back a new block model, all populated nicely with your predictions. And then that means that your mine planning people can quickly use that to do dynamic optimization. If you haven't heard of this before, it's because it's really new. So don't feel like this is really cutting edge for mining. And I'm quite excited as a mining engineer who's been trying to design with rock for all my career, whether it was as a mining engineer doing drill and blast or as rock mechanics engineer trying to stop things falling in. It's been a problem, the uncertainty around our ability to measure the mechanical properties of rock particularly. Yes, I think that's time's up. So thank you very much, everybody. Enjoy the rest of the conference.
Great, thanks very much, Penny. And Penny's company, Petra, has an exhibition stand here, so any questions afterwards, feel free to drop by, and I'm sure the team can help you out. They're just out the door there, actually. Our next presenter is Adrian Boeing. Adrian is the automation manager at Epiroc, and he's here to talk about interoperable autonomous mining. So welcome to Adrian. Thank you.
Wonderful. Yeah, thank you for the introduction. So, Adrian Boeing, the automation manager for Epiroc Australia. If we sort of look at the challenges we have in the mining industry today, you look at any mine site, you see this large, unstructured environment. It's basically a construction site that's constantly evolving and changing. As a result, it's very transient of what you're doing in one place to the next place, so things are always sort of moving around. You have different bits of weird and wonderful equipment that need to come together to try and meet your business objective of moving bits from A to B. And there's a huge amount of variability. We have this uncertainty about the ore body, so we don't know exactly what we're doing. We're discovering it as we go. So there's always going to be this variability in our operations until we have perfect knowledge of the system. And so, that sort of feeds into what are you seeing on the equipment. You're not getting this high level of operational overall equipment efficiency out of the equipment. There's also gaps in terms of, where we are today and where the best practice is. So, what can we do about managing this overall mine, and what tools do we have in our basket to try and improve some of these situations? So, state of the art at the moment is, I guess, autonomy. So we'll pull that tool out of our box and let's give that a whack and see how we can try and improve the situation. So this is a case study here with BHP. So we've got 6 sites in operation in the Pilbara. 5 of those are brownfield sites. 1 is a greenfield, so that's South Flank. It's new, so they just came out straight into autonomy. But the rest of the sites went through a transition from existing manned to being retrofit to autonomous. And it's all being operated out of the central facility in Perth, 1,500 kilometres away. So what does it look like on site? So a few things to look at in this video. So first of all, it's a little bit sped up. So if you look at the top left, you can see the time, and it was done back in 2014. So it's been around for a fair while now. But if you look at the actual pattern, you'll notice it's all very nice and flat. And that's because the drills are drilling to the correct level. So from the previous bench to the next bench becomes nice and flat. Each hole location is in the correct XY spot. It's pinpoint accurate from where the drills are going. And you notice that each hole collar looks the same because they're drilling through to a quality target, so you're getting the same quality result at each time. In other words, it basically looks like a robot's drilled out that pattern. You'll also notice the machine's moving nice and smoothly. It's moved and operated in the way it's designed and intended to be operated. So what that means is, all right, we get a production rate increase. So 16% faster per hole because we're getting faster instant pen rate, but also the overall drill cycle is faster. We get a big uplift in utilisation because we've moved some of that human element in terms of shift changes, other breaks, but also now we can operate through weather conditions. So if there's a cyclone or if there's a blast in the area, you continue to operate. That extra availability gain you get through not having operator damage and operating the machine as intended. So overall, you get this 1/3 increased capacity from the drilling operations. So that lets you do more with less. So it's a good first step, right? It's a good quick win, good first step getting you along to lifting the entire process. But really where you see the major gains is when you look at something like this. So this is a real data graph of what the productive output was from a mine site. So you can see when it was manned, so the production was sort of up and down a little bit all over the place, and it's varied depending on what the particular mood of the operators happen to be and also what the weather conditions are and so on and so forth. As you transition through into autonomy, you can see the productivity drops down a bit because we're taking the machines out of production to go and retrofit them, and then it gets lifted back up to a high level with autonomy. But the really important thing here is you get this nice consistent result. And the reason for that consistent result, again, we've got a robot that's doing its work, and it can only do its work if everybody else in the previous downstream chain was doing their job correctly. So if the planning team's doing the things correctly, the development team's doing things correctly, now you've got this nice smooth process, and you get a nice smooth consistent outcome that you can control. So that takes us to state of the art today. Well, what's the next step? Because there's still a gain to be had. How do we now bring this improvement across all of the mine? So here you've got a typical vision for a mine site, looking at zero entry, no more people on the ground, fully autonomous, fully integrated mine. And why are they chasing that? Well, now you can eliminate that variability across every piece of the silo, bring these different silos and isolated islands of automation together, and you can start to design new mines. With autonomy included, you can look at a different type of mine design. I think we saw that in the keynote at the start of this conference. So if we're going down this path to have this fully integrated and optimised autonomous mine, how do we get there? Well, autonomy is the platform. To get there, we need to have good data on how we're operating today. And to get good, reliable data, you can't rely on people filling in plod sheets, with 15-minute increments and making mistakes. An autonomous system gives you the actual true data of how things are operating. It gives you a nice, rich, reliable data platform. The second thing, as you've seen, is guaranteed compliance to plan. So the autonomous system will do exactly what it's told to do. It can do it in real time and it can do it instantaneously. So it gives you that platform to do that. And it enables the new mine designs. It doesn't make any sense to build a future mine around manned and old mining methods. Future of mining is going to be autonomy, and that's what you want to optimize against. It doesn't make sense to build a faster horse and design a city around a horse that's a bunch of horses running through it, creating manure on the streets, right? You design across what is the actual end state going to be. So the step to get you to a fully integrated, highly optimized mine, first step is autonomy. So the next step, of course, is taking all those bits across to the value chain and integrating together. And I think it's fairly clear that there's lots of value to be had in integrating that mine. You'll see that as a common vision. But the real question then is why does it need to be interoperable? So if we get an integrated system, we can take ourselves from this sort of function-based, drill a hole, to the process-based, tram, level, drill, level, tram, we've got that down. But the next step really is to take it to a goal. All right, I've got a schedule, I want that executed, I want the entire pattern sorted out, go and sort it out for me. That's what the integrated system can deliver. But why do we need it to be interoperable? Well, simply, we want that agility. There's a big value statement. We've seen value statements over $500 million there. You don't want to sit there waiting for individual pieces to come together from one sole supplier. If you have an interoperable system, you have that flexibility. You can bring those different parts together, and as well, you can choose and put together the best of breed. So you can get the best of all the worlds, leverage the innovation, the best of innovation at each individual supplier, and bring it together to give you the best system. And on top of that, to do this optimization, you need information standards. That's not data standards, it's information. You need to understand semantics. To have an interoperable system, each bit of system needs to talk to each other in a way they can understand. So you need that semantic knowledge. And that's what an interoperable system will give to you. So it's fairly clear what are the technical requirements here. We need to find a way to do this safely. It's really important that we do this safely. That's one of the key business objectives. And we need a framework to put these different bits together. But we also need to change the way we do business because, all right, now we're moving to a goal-based technical system. It doesn't make sense if we now try and still do business on a transactional nature. We now have to move to a goal-based business system as well. And if we can do that, as we've seen in some of the previous examples, and as you've seen when you do your studies about what the future of a mine will look like, you can get that increased productivity, you get that reduced cost, but now you're more agile, you're more flexible. So when you move to saying, the future of my mine will look like this, you can marry that up with what does today's mine look like, what today's equipment looks like, and bring those two worlds together and do it faster than you could before. So what's Epiroc's track record in terms of interoperability? We've been a big push on RedEye. It's the most successful interoperability standard that's in the mine today. We've adopted collision avoidance standards already. We integrate our system into other fleet management systems, so you can go and put a Wenco, a Hexagon, or some other system onto our drills, and they'll go and talk to each other. In terms of planning system, you can get a schedule out of Deswick imported through. You can get the drill and blast results and put them through into Maptech, and I'll use that to optimize your blasting. So a lot of people are talking about it. We've kind of had a history in it, and we're doing it, and it's been done already today. And another example of that is our integrated operation system. So we have this, what we call the control tower. It's an example system for us. We can come through, try different things, demonstrate how it works, bringing those different parts of the chain together into one test organisation. And on the autonomy piece, we can see that we're clearly leading in the space there on the blast hole drills. But yep, we've done that function autonomy. Yep, we've ticked that box on the process autonomy, and we're well on our way to achieving that goal-orientated autonomy as well, bringing in all those different bits of asset together into the mine to one cohesive system. And how are we doing this? We're doing this through partnerships. We're leveraging innovation at the best places. So for example, we're working with Saab. They've got a good understanding of critical infrastructure, building systems that need to work. Airports can't shut down. They need to get things coming through. They have a great understanding of cybersecurity, making sure that everything is going to continue to operate in in a sort of a defence environment. ASI is another example. So yes, they have that same sort of defence and security background, but they also operate in more consumer-friendly spaces, so things like the automotive industry, agriculture, and household cleaning products. And so what that does is lets us leverage some of that innovation. Currently, if you're looking at an autonomous piece of equipment, it's an expensive proposition. It's not the same sort of value proposition that you might want to do when you're going buying a household vacuum cleaner. You're probably not going to pay the kind of money you'd pay for an autonomous piece of kit on a mine. So by leveraging some of the innovation and knowledge from there, we can bring down the cost to mining. So that as well allows each vertical to focus on their strength, bring all that information together, and it lets us bring a true interoperable system. So it's not an assimilation of systems into one big end of systems integration piece. It's bringing the best bits from different areas together into an operable framework. So a bit of a more concrete example of how you can achieve that agility and that flexibility through interoperability is through the ASI offering and partnership we have. So up the top there demonstrates the traffic management system. So there's no need to take existing traffic management system or your fleet management system, throw it in the bin. It can be complemented through an autonomous traffic management system. And we can integrate to existing third-party systems. So what does that do? If we think back to our problem state there of this transient and variable mining environment, well, now we have this flexible system. We can go and adapt to what your current brownfields and what your future greenfields vision looks like and bring that transition across. We can start to integrate together and give you a real-time response to changing mining conditions. From the autonomous vehicles, yep, there's some vehicles you can go out there and purchase direct from an OEM, but the goal here is to have a 100% autonomous mine. So that really gets you do the step change, which means there's always going to be a few bits left over. So to address those, we have a retrofittable kit. You can come through and attach to, whether it's a bit of a hydraulically operated machine or if it's a drive-by-wire machine, and get you that 100% footprint. So again, thinking back to our problem statement, we have these large mines, these diverse mines that are going to get more diverse in terms of equipment when we're doing precise mining in the future. We can enable to get that autonomy footprint, do it safely with having these bits working together, and enable that 100% footprint, which enables that step change to a fully autonomous, unmanned mine. Thank you very much. If you've got any questions, head over to the booth because I think I've used up my time. Thanks very much.
Thanks very much, Adrian. Our last presentation for this this session is Alex Urquhart. Alex is an engineer and he's also the engagement manager at RedEye Apps. And Alex is here to talk about visualizing O&M inspection data in 3D. So welcome, Alex.
Thanks very much. So basically, I just want to give you a quick overview, obviously only got 10 minutes, and speak about a current project we're doing with BMA at the moment and their shutdowns for their drag lines. What I want to focus on today is though all presentations, and coming from the engineering world, I try to give something back in my presentations of something of value, something to walk away with, and something practical. So I'll talk about the O&M visualization data we're doing at the moment, but something I really want to focus on, and a great topic hearing everyone today, is making purposeful and cognitive steps towards digital transformation that we treat really seriously at RedEye. So, is it the big one with the arrow. So what I'm noticing now, because with RedEye, I'm lucky enough to work across a bunch of different asset owners, mining, oil and gas, power. And what we find is that with the digital transformation, what the typical scenario in the market is that they get told that, hey, if you don't digitally transform or use your BIM strategy in the next 5 to 6 years, you'll get left behind. So how the topic typically comes back to us is the CEO says we need 3 pounds of BIM really quick or else we're going to get left behind. So we get called to say we have a bunch of wax paper drawings and hard copy data, but we want a 3D model. But realizing that it's a full process. I'm a big fan of patterns in nature. I used to be in the fitness industry for a while, and realizing when someone used to come and say, a very overweight person would say, I want a six-pack of abs, the idea and the concept is great, and we want to encourage that, but be realistic where you're at and understand where your current data is, and try not to eat the elephant in one bite. Take it step by step and make each step purposeful, and most of all, make sure it addresses a problem. One of my favorite quotes from Albert Einstein is, if I knew how to solve a problem, I'd spend 55 minutes thinking about the problem and 5 minutes the solution. We find that if you focus on the problem long enough, you find the solution's quite easy and quite simple to go ahead. So what we decided to do was something with the foundations of a digital twin. In the first instance, it was the operations and maintenance data, being able to do inspections easily from the field. So taking my own medicine, started with the problem first. So the digital twin, obviously having, which Petra had a great presentation today, we find in the assets, for instance, so just the drag line in this case, is how can we go from the data in the field, data back to the office? You've got a great system, the ERP, all your systems back at home, but if the data's not collected properly and doesn't represent what's actually going on, the system's only as good as its data alone. So speaking with a number of the teams through BMA, finding that from the operations to the users to the IT to the innovation department, we sort of found that the biggest problem was getting not only paper, even just digitalizing forms wasn't enough. So we had to replicate the data we're collecting to the data that was actually back in the head office. And we found that large volumes of irregular data was where it was found. So the end goal was to obviously give a visual representation of the data in the field. Again, some of the challenges and why I say take it one bite at a time, there's enough challenges on step 1 without looking at step 10. So step 1 of getting a 3D model on an iPad or your iPhone and being able to find and pinpoint issues, jobs, maintenance, whatever that may be. So the first instance was making a rendered image on the model and training users on how to use it in the field. Part of that was sitting down with the users and saying, what would make sense to you in every step of the way? And every single meeting, there was at least 4 guys that said, it's got to be easy to use, it's got to be easy to use, it's got to be easy to use. It doesn't matter how technical it is or the problem you want to address, it's got to be usable. So a lot of our designs were focused around that. So improving the now, so coming back to what I just said before, so the concept was to build with. So to go through and say, how would it look now, instead of saying on boom number 438, on section 344, that may be different to someone else or recorded wrong, but if I can visually represent that on the actual asset itself and have a timeline of what's coming up, a heat map of all the issues done on, say, the boom, for instance, or the drag line, and how that could be fixed over time. So starting with the now, this is a very conceptual just preview of what the system will look like. A lot of it was developed from like a Facebook, LinkedIn interface, making sure that the guys can use it in the field and not cluttering it with too much data either. So like I said, looking at step 1, don't eat the elephant. for now, we just want a really easy way to pick up data in the field, make it actionable, and get a return on our investment in the first step before we start plugging in all these different systems to our digital twin. Part of that was on the timeline here of seeing what's coming up soon, a heat map of the issues on the boom on this instance, and any sort of associated data. So challenges that, again, you don't really think of until you start working with it is how can we make this rendered image in the field? How can we go offline? Obviously, mines don't have the best connectivity everywhere. How do we make this things like videos and relating that back to maybe the EDMS or your systems back at the head office? And then how do we translate that into actionable insights into the actual asset itself? And then in real time, we want to be able to have the guys sync the data in the field, call them back and forth and say, hey, I'm noticing some more issues at the moment. Can you go back and have a check, please? And again, so with the tablet view itself, we want to try and drill down more and more. So look at the 3D interface, and I think from memory there was 7 levels of asset hierarchy. So ones we can break it right down and really have each part to help preventive maintenance from there on. I think for now that a lot of complex asset maintenance is developed around sort of running things to the ground. So any sort of more additional insights we can have to make it predictable, the better we can set ourselves up. So again, more just a quick overview of drilling down to the binary level of what's there, having offline usage and being able to see, all right, what should happen next as the next step to preventive maintenance. So another thing I want to share, I guess a takeaway, and probably something that hopefully is valuable to everybody here is taking everyone and the key stakeholders on the journey with your digital transformation. So throughout every step of this, it was hearing a problem from BMA and then translating that into what we thought was a solution, but not just running off, developing it over 12 months, spending a God knows amount of money, and then doing a UAT just to find out that, hey, you know what, it doesn't satisfy X, Y, Z criteria. So from the actual vision and the success criteria, we sat down and said, this is what we want, this is what we're thinking, what do you think? And then we modified that around their expectations and their vision of what was acceptable. User scenarios, we looked at user stories time and time again, and even just through the actual user interface and the graphic design. We said, would this work? You know, the way you do, you raise an issue back to the ERP, would this make sense? And finally going through the 3D model strategy with their IT team, then going down even further, down to the final validation. So again, like any sort of project, you've got to have a start, a finish, and then step by step to see how we can achieve that. The most important thing is how do we know if it's a success? Because before we look at going above and beyond with these digital twin projects, we've got to make sure step 1's done properly, or else we're going to be on a bad foundation. So the next steps from here now is, as I said, this was for a drag line for the shutdowns department as a use case. We find this is a really critical area for these guys, but we're going to develop this out further. Processing plants, wash plants, any sort of large complex asset that needs consistent maintenance and multiple dimensions to actually try and get a holistic view of what's going on. Again, we're not kidding ourselves. You know, we understand the mining industry can be quite slow. So again, like I said, in the fitness industry, let's not look at the 6-pack of abs yet. Let's start with step 1 and do it really, really well. And then we'll look at step 2 and maybe integrating additional systems, maybe financial systems and so forth. The biggest takeaway I can say is that anyone you partner with or any sort of developments you have, try and be involved as much as possible. Make sure you're there every step of the way and validating it to make sure that, you know, every innovation, every solution should start with the problem first and then work back. So. And that's it. Thanks very much.
Thanks very much, Alex. And Alex and his company RedEye have an exhibition booth here, so any questions, please feel free to drop by and ask the guys. I'm sure they can help out. That's the last presentation for this session, so we're now moving back into the main room where we have 3 work streams, so please enjoy. Thank you.